name is Frank Sanders. I'm the head of the Telecommunications Theory Division at the Institute for Telecommunication Sciences, a laboratory of the National Telecommunications and Information Administration, NTIA, located in Boulder, Colorado. Over the past 30 years, we've developed a series of techniques for measuring emissions from various types of radio emitters. In particular, we've developed techniques for measuring emissions from radar transmitters. In this series of talks, I will begin by describing the fundamentals of RF measurement techniques, and I will culminate the series by describing our techniques for measuring emissions from radar systems, techniques that hopefully you can implement yourself. Accompanying this series of talks are notes available on our website and also NTIA reports that you may find useful. We hope that you will enjoy watching this series of videos as much as we've enjoyed producing them. Welcome to number 5 in the series of RF seminars. The topic of this seminar is amplifiers, noise figure, and dynamic range. What we're going to talk about is how to measure a signal that is weak or low compared to the noise figure of a receiver or a measurement system of some sort. In this talk, we'll be using quantities that are both linear and quantities that are decibel. The convention that I'll use is that linear quantities will be written in lowercase. For example, gain, if it's linear gain, will be lowercase g, and decibel quantities, which are 10 log of the linear quantity, will be written with the same Roman character but in uppercase. So here's the problem that we're going to address. Suppose that we have a measurement system or a receiver of some sort that has a particular noise level, like so, and we're trying to measure a signal which is down here, and just to make this an easy example where this is power in decibels, is that if the noise power of the signal that we're trying to measure is just equal to the noise level of the receiver, then how high above the noise will we see the signal if we're running a measurement system that sums the power of the noise and the power of the signal? Well, 3 dB, as we've discussed in earlier talks. So if the actual signal level is here, we'll see the signal 3 dB above the noise, like so. And we remember that we have to be cognizant of the fact that if we're using a measurement system and we see a signal that's, say, 3 dB out of the noise, that means that its real power level is in fact equal to the noise power. And you can do the math, of course, for other values like, say, 1 dB out of the noise or 4 or 5 dB out of the noise. We don't have to worry about doing any kind of a correction once we see the signal 10 dB or more out of the noise approximately. Now, what we'd like to do is be able to do a measurement on this signal in which we see the signal itself roughly, say, 10 or 20 dB out of the noise. This allows us to more easily do an accurate power measurement without having to do this kind of little correction. And it also means, of course, that we can see additional features in the signal structure like this that we wouldn't be able to see if in fact we could only see, as it were, the tip of the iceberg, tip of the iceberg sticking out of the noise. So, noting that this is our noise level, what we're going to do is develop this as a mathematical theory. What we're going to do is consider a situation in which we have a measurement device, say a spectrum analyzer, and at the input to the spectrum analyzer, we're going to install an amplifier. Actually, I'm going to draw the amplifier slightly bigger. We're going to install an amplifier like this at the input to the spectrum analyzer, and we're going to imagine that at the input to the spectrum at the input to the amplifier, we have placed a terminated input, a resistor, say, which itself is producing electron noise at a level of kTB. We've discussed this in earlier talks. And then, inside this amplifier, we imagine that we have two components, and what I'm drawing here is the so-called lumped component model for amplifiers, in which we have one unit that is a pure gain component, and we have another unit which produces some amount of noise, which is completely inescapable, and that we have a summing circuit which sums the power in the pure gain stage and the power coming out of this noise stage, and that it is the pure power coming out which is in fact sent into the spectrum analyzer. And I will connect the input here to the pure gain stage. Now, the gain stage represents a mathematical multiplication, and we're going to take whatever comes in at the input to the amplifier, we're going to multiply it mathematically by this linear factor g, lowercase g. We're going to run that amplified, multiplied, that is to say, factor out through this amplifier output, but unfortunately we're also going to inescapably generate some amount of noise in the amplifier, and that noise is going to be summed with this amplified signal, and that's what we're going to actually see in the spectrum analyzer. So let's look at what we see. What we see in the spectrum analyzer, what we have here is a certain noise level at the input and a certain signal level at the input. This will be N sub I. This will be S sub I at the input. And when I talk about input, what I'm referring to here is this point in the system. Now, what we're going to generate at the output is a higher signal level, something that looks like this, and also a somewhat higher noise level, like this. So here's N sub O for N sub output and S sub O for S sub output. But what we're striving to obtain is a situation in which this ratio of signal input to noise at the input will not be as large, or will be enhanced at the output with a larger ratio of signal output to noise at the output. So we're going to have a quantity here that we define as noise factor. And the noise factor is equal to signal at input divided by noise at input divided by signal at output over noise at output. And this forms the jumping off point for the rest of the discussion. Okay, so to continue. So these quantities, SI and NI, signal in, signal out, where noise out is the amplified level of signal in plus a little additional noise added, hopefully a little additional noise added, can be put into a mathematical term, noise factor, which is the input signal to noise ratio over the output signal to noise ratio. And of course, the way that I've written this is linear. Now, for the record, and we will use this later, there's a second quantity, noise figure. And by the way, the terminology I'm using here, I believe, does follow IEEE conventions, which is equal to 10 log of the noise factor, NF, equals, and in capital NF, like so. 10 log of that, which of course is 10 log of the input signal to noise ratio minus 10 log of the output signal to noise ratio, like so. Just for So we'll flip back and forth between capital NF, decibel, lowercase nf, noise factor versus noise figure. But that's all that's going on there. I want to label these equations, and we'll label this one equation 1A, sorry for the squeak, and this one we'll label equation 1B, just for some future reference. We can flip back and forth to these. If you're taking notes, you can note that as such. Okay. Now, keep that board in place for the moment. Something left over from last time. Sorry about that. Okay. Okay, so, all right, so going back to linear terms, the signal out level is going to be equal to G times the signal input level, and the noise output level will be equal to G times the noise input level plus NA. And that means that since noise factor is equal to SI over NI divided by SO over NO, that is in fact equal to SI over NI divided by GSI divided by GSI over GNI plus NA. So far so good. And that's equal to SI times GNI plus NA divided by GSI. The SI's divide out, and that gives us GNI plus NA over SI. So far, so or over GNI. Sorry, over GNI. Make sure I've got that right. Plus NA over GNI. Yeah. Yeah. Am I not right?
And the second one, you didn't have the underneath.
Oh, let's see. SI. Oh yeah. Sorry. Got it, right. Thanks, Teresa. Yeah, there we go. Okay, so far so good on that. And we'll call that one, just to refer back again, that's our little equation 2 right there. All right. Now, for a circuit at temperature T, and of course, T room temperature is equal to 290 K. The input noise is going to be equal to KT. That's the energy density per hertz. Remember that K is equal to 1.38 times 10 to the minus 23 joules per Kelvin. Another way of writing K, or actually KT, is that this quantity is minus 204 decibels relative to a watt per hertz, which is equal to minus 174 dBm per hertz. That's the quantity here, and then we can multiply that by B, the bandwidth in which we actually are running a measurement system or making a measurement, to get the actual power level that would be produced. But this is considered to be the noise input power level for an amplifier sitting here at room temperature. So noise factor now is equal to KTBG. We've got the NI, KTB, times G, plus NA. Try to make that A a little clearer. There we go, plus NA. Divided by GNI, which again is KTBG. And again, bear in mind that if you ever need to, you can take the bandwidth out and just work in spectrum power density, or you can leave the bandwidth in and work in actual power levels. It's not going to matter in the end which way you go with that. We'll call this, and there's our little equation 3. And so one thing to note here is that this noise factor is basically equal to the power out divided the noise power out divided by the noise power in. The way that we've put this together. Now, suppose that what we're going to do is actually set up a system, and I want a little more room for this. I'm going to keep this board in place. I wish I had more boards. I'll have to erase the first board, but or at least part of it. I'll keep the equations at the bottom and erase everything here up above. I need a little vertical room. Leave that equation. Sorry. All right. Now. Okay. So now we're going to set up a little system here. And in this system, we're going to set up a little circuit with an amplifier, like so, going into a second amplifier. We're going to come up with a generalized expression. We're going to come up with a generalized expression for how a set of amplifiers will behave, or for that matter, a set of two-port devices, which could include amplifiers, spectrum analyzers, attenuators, etc. But for the moment, we'll put two amplifiers in series with each other, and you'll see where I'm going with this in a moment. And the term that is used for these is cascaded, which just means that you've got one running into the next. And so, here, at the input to the first amplifier, we've got a circuit at a temperature T, probably room temperature, KTB, is what it's producing. And this is at the input to the whole system. And we're going to look at some quantities right here, okay? And then we're going to look at some quantities here at the first output. And then we'll look at some quantities at the second output. Like so. Okay, like so. So here, the power that's present in our system is just KTB on this side of the input to the amplifier. Now, when it goes into this amplifier, which has a gain characteristic G1 and which has an additive noise characteristic NA1, what are we going to produce at the output, right here at the output? Well, it's going to amplify the input KTB by this factor G1. So we amplify, it amplifies, we get KTB G1, and then it adds, first it amplifies, then it adds a quantity, and A1 like that. Now, this power goes into the next amplifier that has some gain characteristic G2, and which has some additive noise characteristic, the amount that it adds, which is added noise sub 2. And what it's going to do, of course, is first of all amplify its input by a factor G2. Well, what's its input? Well, since the total output here was KTB G1 plus NA1, like so, that's its total power output. It's going to take this quantity, multiply it by G2, so now when we write what it's doing to amplify, it amplifies, and so now we get G2 times this quantity, KTB G1 plus NA1, and then it adds additive noise level 2, and so the total power that we get out of this stage right here, we'll call this output 1, call this output 2. Output 2 is going to be equal to. I just want to make sure that I write this the way I want to. Is going to be equal to G2 times KTB G1 plus NA1 quantity plus NA2, and that's what's flowing out right there. So there's a pattern developing, and of course we can now continue this pattern on down the line for additional components. So we can go ahead and simplify this. Output of the second stage is going to be equal to G2 times KTB G1 plus NA1. I'm just rewriting this, plus, and now outside the brackets, NA2. All I did was rewrite that just now. And that in turn is going to be equal to KTB. I'm going to pull the KTB G1 out. KTB G1 G2 multiplied by 1, right there, right? Pull that out. Plus NA1 divided by KTB G1 plus, and now I'm going to bring the NA2 in, NA2 divided by KTB G1 G2, if I'm looking at that right. Yeah, so far so good. Now I'm going to, I'm running out of room here, so I'll go ahead and erase these. I just want to keep them up there for a moment. All right. Bracket. Okay, like so. Now, I'm going to say, but since we're just going to, if we just do the algebra for the noise added 1, NA1 is equal to KTB G1, let me make sure, yeah, times noise figure 1 minus 1. And this thing else I want to note here, this amplifier has a noise figure NF1, and this amplifier has a noise figure NF2. And and what's the next part? I want to make sure we get the, oh yeah, and then NA2 likewise is equal to KTB G2 times noise figure of the second amplifier minus 1. So for any amplifier, of course, you see what the pattern is going to be here. And that means that the output, this output level, I'll draw a red line around like this. And so this output level, to come over to here, the output, like so, is equal to KTB G1, G2. Always pays to do the math in advance to make sure that I'm getting it right. Times noise figure 1 plus noise figure 2 minus 1 divided by G1. Right, there we go. I'm just checking to make sure that's right. Yeah, okay. So all we've done is algebra. And this will be equation, make this equation 4 right there. So what we've done is to render this thing in terms of noise figures instead of noise added. That's all we did between this step and this step. Just to render it that way. Now at this point, I'm going to take an inductive leap, an inductive step, and generalize this out for n stages, and I'm going to write this right up here. So for n stages, where this is stage number 1, this is stage number 2. Now we'll go all the way out to any arbitrarily large number of stages n. So for n stages, the output, I don't like this pen, I'm going to use a different one. For n stages, the output power, that's not good at all. Try this one. Output power is going to be equal to KTB, I'm going to write it down here actually, give myself room, KTB times G1 times G2, etc., all the way out to G sub n. This is the part that comes out in front. This is the amplification part of the equation. This, in a certain sense, is the good part. That's the part we were looking for. We want to amplify signals. These are linear quantities, so we're just multiplying all these gains. So here's the amplification part of our equation. Just keep multiplying the gains on out forever. And then comes the penalty phase of the equation. I'm going to erase this little part right in here. And the penalty phase is the noise factor part. We have to multiply that by the noise factor of the first stage, NF1, plus NF2 minus 1 divided by the gain of the first stage, plus noise factor, I'll go noise factor 3 minus 1 divided by the gain of the second stage. So the gain terms lag one behind the noise factor terms, plus, and now the pattern continues out here indefinitely, and unfortunately I have to erase this little part right here, plus all the way out to noise factor of stage n, the last stage, minus 1, divided by the gain of the next to last stage, G sub n minus 1. Just want to make sure. Oh, sorry, sorry, this is G1, G2. We keep multiplying the gains, right? This would be G1, G2, G3, etc., out to G sub n minus 1. There we go. Out to G sub n minus 1. There, sorry about that. Yeah, okay. And this is a really important equation. It was developed in the 1940s by an engineer scientist named Riis, R-I-I-S. This is the very unhappy cascaded amplifier, or really, it's not even cascaded amplifier. It's really a set of cascaded two-port components, but typically it's used with the amplifiers equation. For gain noise figure, noise factor, like so. And where I said that this was the bonus part, this was the amplification part of the equation, this is the penalty part, which is the additive noise that those generators are creating, that those amplifiers are creating. Now, so having said that, I'm going to erase this part right down here, and I'm going to break this thing apart into its two constituent components. So what this means is the noise factor of your entire system, the entire cascaded system, the noise factor of that system is this part of this equation right here, which is the noise factor. I'm going to noise factor. Sorry, there we go. Noise factor of the first component plus noise factor of the second component minus 1 over G1 plus noise factor of the third component minus 1 over G1, G2 plus noise factor of the nth component minus 1 over G1, G2 up to G sub n minus 1. Okay, so now we have an expression, an equation that tells us what the noise factor for this whole overall system is going to turn out to be. And I want to call that's an important one. That's equation number 5. And incidentally, the amplification, which for our purposes is not all that important, the amplification for the system is equal to KTB G1, G2, etc., up to G sub n. So this is the important equation that I actually wanted to get to. Now, initially, what we'll do in the lab, and what we usually talk about, is a fairly straightforward, fairly simple system in which the first component that we'll have will be an amplifier, and the second component will be a receiver or an instrumentation like a spectrum analyzer. But it is important to set this up and cascade it, and you'll see why in a minute, because we'll need to apply this to lots of additional cases. Does everybody have that for the moment? If anyone doesn't, let me know. Otherwise, I'll bring the board forward in a second. All right, I'm going to bring the board forward, and in fact, I'll just reproduce this and let's figure the system. I should do billboards for a living. Imagine if you just put that on a billboard. What would people think? So, again, I'll just reiterate this here so we have it. Noise factor for the system is equal to noise factor 1 plus noise factor 2 minus 1 over G1 plus noise factor 3 minus 1 over G1, G2 plus, and so forth, all the way up through noise factor n minus 1 over G1, G2, G3, etc., up to G sub n minus 1. Okay. For the system. That was our important equation. Now, remember that this is a linear equation, but when we have amplifiers, like, for example, one of these, a low noise amplifier, and these two that we're going to use today have definitely been through the war, but they still work really well. We're working in decibel terms. So, let's suppose that our system looks like this. We have an amplifier going straight into a spectrum analyzer, and the noise figure, capital letters, decibels, noise figure of the spectrum analyzer is equal to 25 dB, a good typical number. And we'll suppose that this amplifier's gain, again in decibels, capital G, is equal to 20 dB, and its noise figure in F, remember that's the additive noise in decibels, is equal to 5 dB. You'll see in a moment that I have not picked these numbers accidentally. Let's work through this and see what we get here. So what this means is G1, if the gain is 20 dB, what is G1, the gain of this amplifier here? What would it be in linear terms? Divide 20 by 10, and you get 2, and then take 10 to that power. So the linear gain is a factor of 100. So G1 would be a factor of 100. And I won't make you do the math on this one. If we want to get its noise factor in F sub 1, that's going to be equal to this number divided by 10 and taken to the 10th power. So it's 10 to the power of 5. Actually, you can do the math on this. 10 to the power of 5 over 10, 10 to the power of 5 over 10, which is 10 to the 0.5, which is the square root of 10, which is 3.16. Okay. So what we just did was to translate from what you see on the side of the amplifier, you see in a lookup sheet, into the linear terms, which people don't do very often. Now over here, since noise figure 2, this is noise figure 1, noise figure 2 is equal to 25 dB, that implies that noise factor 2 must be 10 to the power of 25 divided by 10, which is 10 to the 2.5 power, which is going to be 316. Ooh, you can already see that why I didn't pick these numbers accidentally. There's something going on there. Okay, so that means that the overall noise factor for the system is going to be NF system. Okay, so we just start right here. It's really easy. That's NF1 plus NF2 minus 1 divided by G1. Like that, okay. Noise factor 1, 3.16 plus 3.1 plus 316, right? 316 minus 1 divided by G1, G2, right, which is, divided by G1 divided by 100, right, sorry. Yeah, thanks, Teresa. Right, okay. So that's 3.16 plus 315 over 100, which is 3.15. And that's equal to, basically, that's equal to what? It's equal to 2 times the original noise factor, which is 3.16. We're just adding these two numbers up twice. That means that the noise figure for this system will be equal to noise figure number 1 over here. Noise figure number 1 over here corresponds to the 3.16 number. The noise figure number 1 plus 3 dB. Okay. What did I just do? What I just did was create a system in which the gain plus the noise figure of the amplifier summed the sum of the two in decibels, which is 20 plus 5, equals the noise figure of the second item in the cascade, which is 25. And I'll do the proof here in just a second. But if you set it up like this, such that G1, this is G1 plus noise figure 1 is equal to noise figure 2. If you set things up that way, then what will happen is the excess noise that this amplifier produces when there's no signal source present, nothing but thermal noise here at the input, KTB, KT in density, here at the input, what will happen is the power that this produces out of its output will just be equal to the noise, the excess noise power the spectrum analyzer itself is generating, and when we add two equal power levels, what happens? It goes up by 3 dB. So that's what I just did here with the math. So if we can also just work this out directly. 2 times 3.16, we can take 10 log of 2 times 3.16, or we can take 2, and that is equal to 8 dB, which is in fact equal to 5 dB, which was noise figure number 1, plus the 3 dB, which was the result of producing just as much noise here. And I mean, check the math if you don't believe me, but take 10 log of 6.32 and you'll find this 8 dB, which is the original noise figure 1 of 5 dB plus 3 dB. It all works out. I'll give you a preview. That is where typically a person who's designing a radio receiver or a measurement system wants to be with a cascaded series of components. They would like the gain in decibels plus the noise figure in decibels of a given component to be just about equal to the noise figure of the next component in the cascade after that, and so on down the line. If you can design it that way, and we'll see in a minute, you will be able to get most of the benefit of that gain in terms of seeing an amplified signal, and yet you won't eat up, and we haven't talked about this yet, much of the dynamic range of the next component in the series. And so you'll see this with well-designed radios over and over and over and over again. And I'll also tell you where people can go wrong with that. Now, I'm going to flip to the next board here. I want to do this as a quick proof, and there's a reason I want to do it, because when we do the math on this, we'll be able to see a couple of other interesting things come up. And one of them that I'm about to show you is why you don't need any more gain than what I just showed you. And I'll digress for a moment. People often think that if they want to see more signal, they need more gain. The problem with that thinking is you don't need to see more signal. You want to see normally, a higher signal-to-noise ratio. There, as we'll see here in a moment, the problem with having more gain than you need in the system is that because the gain and the noise are both basically going up together, plus a little bit of added noise, is that at a certain point all you're doing is making the signal and the noise go up higher and higher and higher and higher and higher like this, while you're approaching the top of the dynamic range of your measurement system up here. You're eating up that dynamic range, and in fact you're getting no benefit in terms of seeing your signal any higher out of the noise than you would have had you been using a lower gain figure. And yet this is a mistake which people have been known to make at one time or another, imagine. So before we go to the lab, one last remark I wanted to make was that given that this is our equation, this has one more important result to note, which is that the loss in any component that we stick into the system out here in front of the LNA, in this case this line loss as we've drawn it here, whatever that line loss is, whatever that attenuation is, whatever the loss is in a filter that you put in front of the amplifier, that loss adds directly to the noise factor of the system, which is pretty intuitively obvious. But this is one of the reasons why designers in some cases may resist putting a bandpass filter into a receiver front end. They know it's a good practice to do it for a variety of reasons, but they know that whatever the loss in that filter is, it's going to add directly to the losses in the rest of the system. Likewise, if we're connecting the system up to an antenna and we have a long line going up here and the line has a lot of loss in it, that line loss is going to add directly to the noise figure or the noise factor of the system. So what people try to do is use the lowest loss lines possible or the shortest lines possible, and if they do need to put a filter in, they'll try to get the lowest loss possible in the filter and so forth, because whatever those are, we can imagine a filter along with a line, along with maybe even something else in it. All those losses add up until we finally get to the low noise amplifier. And then of course someone could say, why not put the filter after the amp? Well, that would defeat the purpose, wouldn't it? We'll talk about that at a later, in another talk at a later date. So just something to note here about this.
Hey Frank?
Yes?
The gain of your antenna, does that add?
Ah, good question. But what about the gain of the antenna? Antenna gain is one kind of gain that comes basically without any cost other than the size and heaviness of the antenna. The antenna gain is a geometric factor, which means that you're coupling energy preferentially from a single direction in space, and that gain comes without a concomitant increase in some kind of background noise level. As a matter of fact, if you're trying to look at a distributed energy source like the cosmic background radiation, or for that matter the microwave oven radiation that comes out of a big city area like, say, Chicago or Denver, Washington, D.C., the antenna, as you bring up the gain, gets more energy from the background right inside the antenna beam, but it discriminates against energy coming from all the other directions. So you don't collect any more energy from a distributed background source in a highly directive beam if the source is distributed across the sky or across a wide angular distance than if you were using an omnidirectional antenna that got energy equally from all directions. But if you're getting energy from a point source, a single transmit antenna somewhere, or a single, well, just any single source, it could be a quasar, it could be a radio star, it could be anything. If it's a discrete source, as this beam gets tighter and tighter, you will see the energy from the discrete source at a higher and higher level above whatever the cosmic or environmental background noise might be, assuming that the noise is coming from a distributed area. This actually came up once. People want to know if I could see microwave oven emissions at a higher signal noise ratio if I used a high beam antenna up on a high gain antenna up on a mountaintop. And I said, I explained this on the phone. I said, it's not going to do any good. And they said, Frank, try it. And I said, okay, I'll try it. So I did, and sure enough, I didn't get any more, because what happens is you get more gain on the distributed energy that's inside the beam, but you lose all the energy that's outside the beam, and it turns out that the two factors exactly offset because gain is a geometric factor. However, had I been looking for, or if I am looking for, energy from a discrete source, like say a radio that you may be transmitting with down here in Boulder, then what will happen is I will get more energy coupled into my measurement system from that discrete source out here, because it's a point source, basically a point source, that's in effect located at an infinite distance, and so that is gain that antenna gain is gain that comes without a cost other than a bigger and heavier antenna. So if you want to get more signal out of the noise in a spectrum analyzer and you're looking for a weak signal and you think that you can set up a more directive antenna to look for that, by all means do it. By all means do it. On the other hand, if you're doing a generalized spectrum survey, let's say, where you want to see signals coming from, say, aircraft distributed all over the sky, or from microwave ovens distributed out in front of you, or from land mobile radios that may be distributed out in front of you, then going to a high gain antenna really isn't an option, because the whole point is you're trying to see over a wide set of azimuths spatially. And now if you say, but I want to see more of these signals, what are you going to do? Now you have to go back to getting a lower noise figure on your front end. But, yeah, but all other things being equal, you go to a high gain antenna. And of course people do that for communication systems if they can set up a point-to-point link. There are a lot of advantages to that. Although there is one little mechanical disadvantage. As antennas get bigger and heavier, they get harder to point, and they get more sensitive to vibration if there's a little bit of vibration in the mount. So you get this ultra huge, mega 3-meter dish antenna, and you find out that you can't hold it steady, and the signal's fluctuating up and down, and you back off to a smaller antenna then. But that's just a practical limit, not a theoretical limit. If you're the US government, you just buy a bigger, heavier mount and keep going. The frequency for the spectrum analyzer, we'll say 1 gigahertz. The input attenuation, I'm going to go to attenuation level of 0 dB, okay, like so. Span, we'll make it 10 megahertz for good measure. Detection, we'll make it RMS average. Bandwidth, we'll set the bandwidth to 1 megahertz. And we're about done with our little mental checklist. We'll set the sweep time here to, say, 50, all right, 500 milliseconds. That might be a little slow. That'll be all right. Okay, so we just went ahead and did our quick setup. We set the bandwidth to 1 megahertz. Video bandwidth is equal to or greater than the resolution bandwidth. Sweep time is a little slow, but we're using RMS detection. We switched off the attenuator at the front end. Now we just saw from the cascade gain equation, whatever that attenuator level is at the front end of the analyzer, that's going to add directly to the analyzer's noise figure. So now the analyzer's noise figure is as low as it can get without turning on its own internal LNA. And there is an internal LNA, but we're not going to use that right now. We just want to see how this behaves without it. Everything we did applies to that internal LNA. The only difference is it's on the other side of the little bulkhead connector here. Okay, so what's the level of the internal noise here? 20, 30, 40, 50, 60, 70, 80, 90, about 93, about minus 93 dBm. And so I'm going to turn on a carrier wave here that is at minus 93 dBm. And we should see this come 3 dB up out of the noise, just like so. And it hits right on minus 90. Okay. But someone said, okay, what I'm looking for is a little more signal-to-noise ratio for the reasons we talked about before. We want to see more of the detail of the spectrum. We don't want to have to do the anti-logs to get back to what the actual power levels are as we're trying to measure signals down this low, and so forth. So, someone says, all right, well, I think we can do that. We'll get ourselves an amplifier here. So we'll momentarily disconnect the signal generator from the spectrum analyzer. We'll connect the signal generator to the input of the low-noise amplifier. The low-noise amplifier has to have a power source. It doesn't run on wishes. It likes to have about a 15-volt, okay, that's probably okay. Get that going here. Slightly cheesy clip lead connection for power, but all right. And now we'll hook up the output. Oh, and in fact, I'm going to momentarily turn off the, I'm turning the signal off on the generator for the moment. We're going to turn on the amplifier, and I'm just going to push the connector on and off here. Here is the spectrum analyzer noise floor with no amplifier on it. Now, I've turned on the amplifier. There's no signal input on the amplifier whatsoever. So now this amplifier is generating excess noise, which in decibels is equal to its decibel gain level plus its decibel noise figure level. Oh, and that's one other thing that we ought to do here real quick, is know what the noise figure of the spectrum analyzer is. Well, we're in a 1 megahertz bandwidth, so KTB is going to be equal to minus 174 plus 10 log of a million,
which is 60. So minus 114 minus 174 plus 60 is minus 114 dBm RMS. But this is at minus 93. What's the difference between minus 93 and minus 114? 21, right? Minus 1, 21. So we know that the spectrum analyzer right here is running with a 21 dB noise figure. And we didn't need a noise figure meter to figure it out. Now, I connect the spectrum analyzer and thread the connection on, and we saw the noise go up. Now, this is the part that begins to confuse people sometimes. I turned on an amplifier and my noise went up. What's wrong? I wanted my noise to go down. Your noise did go down. It only looked like it went up. You're seeing the noise in the amplifier multiplied by the gain of the amplifier, which lifts this low noise of the amplifier up to a higher level, but the noise level itself is lower than the noise level of the spectrum analyzer. Was that sufficiently confusing?
Yeah.
You're looking at the low noise of the amplifier multiplied by its gain factor, plus a little bit of additional noise that the amplifier added in. Now we saw the signal level here, and I'll turn on the marker. Okay, it went from minus 93 to minus 86, so it went up about 7 dB. So we know that the gain plus the noise figure of this amplifier is equal to more than the 21 dB noise figure of the spectrum analyzer. If the gain plus the noise figure of this amplifier were equal to 21 dB, that level would have gone up 3 dB. As it was, it went up about 7 dB. So gain plus noise figure here is a little higher than that. But that's all right. That just means that the overall noise figure level that we're looking at here is actually nearly equivalent to the actual noise figure of this low noise amplifier. Now, I haven't touched the vector signal generator except to turn off the signal it was transmitting. Now I'm going to turn it on, and where before we had a 3 dB signal to noise ratio, now we'll see what the new signal to noise ratio is. RF on. We'll hope we see it. And now we're seeing a signal to noise ratio that's equal to about 16 dB. Okay, and I didn't have time to really go through this myself before the talk, so I'm going through this with you. Okay, so we've gone from having a signal out that was just equal to the noise level in a spectrum analyzer, and the spectrum analyzer has a 21 dB noise figure, to the same signal level being 16 dB above this background level. And we know that any time that the signal level is more than about 10 dB above whatever the background level is, we don't really have to do the anti-log corrections on the measured power. We can take it as is. So we have improved the signal to noise ratio here by about the difference between 16 versus 3, so we've improved it by about 13 dB improvement in signal to noise ratio. Now, this is where someone says, ooh, if a little gain was good, a lot of gain ought to be better. So now, I'm going to take the first amplifier out of the circuit entirely, and I'm going to put this into the second amplifier. The second amplifier may have a little lower noise floor than the first amplifier, but it's got a lot more gain.
Would you say the gain of that first?
Oh, in fact, here's what I have to do. The gain on this amplifier is nominally about 30 dB. In fact, I'm going to go back and save this trace momentarily. I want to save the trace. Actually, here's what we're going to do. We'll say trace 1 view. Okay, that's the noise with no amplifier. Now we're going to go to trace 2, clear right. Okay, we're going to turn on this first amplifier, the one we just looked at. Okay, like so. Power on. Okay, trace 2 view. Okay, so now we see spectrum analyzer, initial state. Now we turn on the amplifier. This amplifier has about a 4 dB noise figure with 30 dB a gain. So we're seeing now the noise of the amplifier, not the noise of the spectrum analyzer here, and the signal level, which previously. Oh, and that's one other thing I should do. Sorry about that. I'm going to do one other little thing here for the baseline state. For the baseline state, I'll do that with the signal on. Okay, baseline state, signal on. Back to trace 1, and they say guys can't multitask. There we go. Save, view. There we go. So there's our first signal, barely coming up out of the spectrum analyzer noise. Here's the same signal coming 16 dB out of the low noise amplifier noise. So far, so good. Now we trade out the first amplifier. We're going to go to the second amplifier, which, Yay, do you remember what the noise figure was on this one? It's still about like 4 dB, I think. It's about the same noise figure. It's about 4 dB noise figure, but more gain, because some people think you can't have too much gain. And I'm going to show you that you can have too much gain. Okay, now, oops. Best left alone. There we go. Turn on the power source. Okay. Oh, and now, always helps to go to trace 3 clear right.
Input the spectrum analyzer.
And input this. Oh, hey! Glad someone was paying attention. It sure as hell wasn't me. Okay. All right, now. Okay, now what's happened? What's happened is we're looking at the noise floor of the second amplifier right here. Now, before we had about, 16 dB of signal noise ratio. We now have about 20 dB of signal noise ratio. There are 2 reasons for that. One is the noise floor, the noise figure of the second amplifier is a bit lower than the noise figure of the second amplifier. Plus, with the additional gain, if we go through the cascaded gain equation, we'll see that we are actually approaching an overall system noise figure that's a little bit closer to the actual amplifier noise figure. But look at the price that we paid. In order to buy ourselves another 4 dB of signal to noise ratio, we lost that much dynamic range. We lost about 16 or 17 dB of dynamic range, because as this noise level goes up, the overload point on the spectrum analyzer is not going up. The overload point is up at about here. So we went from having about 10, 20, 30, 40, 50, 60, 75 dB of dynamic range when we started with no amplifier, to having about 10, 20, 30, 40, 50, 68 dB of dynamic range with the first amplifier, which means we didn't lose much dynamic range, but we bought ourselves a lot of signal to noise ratio right here, to then going to even more gain, but with only a marginally better noise figure, and now we're down to 10, 20, 30, 40, 50 dB of dynamic range, and we didn't buy ourselves more than, at the most 4 dB, maybe not even that, of increased signal noise ratio. So now we're hitting the point of diminishing returns, and this is where, as I said, people stick in an amplifier or even a set of amplifiers with even more gain. They buy themselves no more signal noise ratio than they had to begin with, but the dynamic range just finally squeezes down to nothing. Now, at a later date, and of course what this whole series is leading up to is how do we measure radar signals? Well, when we measure radar signal, we need all the dynamic range we can get. We need every dB we can get out of the system with the best possible noise figure. So this is not a good way to do things with this second amplifier. But maybe all is not lost. As I said before, suppose that some guy bought this second amplifier, and you go, gosh darn it, it's got too much gain. Guess we're going to have to buy another amplifier. No, you don't. That's fine. You don't need to buy another amplifier. All we need to do now is put that attenuator in between the amplifier and the front end. Now, we could go through the math and get the exact correct attenuator value, but why bother? We can do it this way. What we'd like to do is bring this down about 15, give or take 15 dB right here. So, I've got a 10 dB attenuator, and I've got a 3 dB attenuator. That makes 13. And let's try another 3. Make sure that's the right one. I lined these up and then I knocked them over. Yeah, so here's 16 dB. So here's 16 dB of attenuation. And I'm going to put this little 16 dB attenuator in between. I'm going to turn this off momentarily. Put the little 16 dB attenuator in between the output of the amplifier and the spectrum analyzer input, just introducing that loss. And so this in effect, putting this attenuator in here is going to effectively reduce the gain of this stage.
Could have done the same thing by just putting attenuation on the analyzer.
Right, and I could, good point. Steve just pointed out, you could do the same thing here by snapping an attenuation on the analyzer, which is absolutely true. In fact, we should do that. We'll do that, just to show it's the same thing. Right, because the attenuation is right at the input of the analyzer, so it's the same difference. This is something that you'd do more if you had a receiver circuit where you didn't have built-in variable attenuation, but you're right, Steve, that's absolutely correct. People usually don't think that turning on attenuation in the spectrum analyzer input, it will give them a better measurement, but this is a case where it will. Okay, so now I've just cranked in 16 dB of RF attenuation. I'm going to turn the amplifier back on again. Ha! Came pretty doggone close. And so now we're back to having pretty good dynamic range, and also because this does have a little lower inherent noise figure, a little better signal to noise ratio. So that's getting close to being kind of optimized. I could stick in another 3 dB of attenuation right here, what's going to happen if I do that is we're going to start to lose a little. And I'll just turn this off and play it safe. I don't want to dink up the power connection here. I'm going to put in, actually my next attenuator is a 4 dB attenuator, so we're going to go from 13 dB of attenuation to 17 dB of attenuation. Now, we're going to get a little dynamic range back, but we're going to start to lose some signal to noise ratio relative to what we had before, if I'm doing the math right in my head anyway. Okay, screw these attenuators together. This is a definite mess. Real mess. There we go.
Mismatch loss?
Oh, yeah. Mismatch loss is all the NTIA doesn't worry about that. NIST only worries about mismatch losses, not NTIA. The more mismatch, the better, I say. You metrology people and your mismatch. Okay, so now what happened was by putting in that next 4 dB of attenuation, just what I said, we didn't really buy ourselves more than maybe another a dB and a half of dynamic range. The purple is maybe a dB and a half below the cyan now, but the signal noise ratio went back down to being about 16, maybe 17 dB. So that last 4, it's debatable whether you'd want to put in that last 4 dB of attenuation or not. Maybe yeah, maybe no. That's right in the gray zone. You could go either way. You wouldn't be marked wrong either way, but you don't really need to put in that last 4 dB of attenuation. And then Steve, I'm going to take you up on your suggestion. I'm going to take the attenuators out of here, go back up to the first state, and we'll do it a dB at a time with the spectrum analyzer's built-in attenuation, which is oh so handy to have, because this spectrum analyzer allows you to vary attenuation a dB at a time, which older analyzers don't. Older analyzers force you to snap in 10 dB at a time. And you could do that here, but then you'd have to choose between 10 dB versus 20 dB. But we don't have to do that. Here we can go a dB at a time. Okay, so now I'm going to turn this amplifier back on with no attenuation. Okay, so we're back to the situation here where we've got a nice signal noise ratio, but we've got a nice signal noise ratio here, but we're losing dynamic range by having this noise level be a lot higher than we need to be right here. Gain, noise level is gain. So now we go to the spectrum analyzer, amplitude control, attenuation, and now I'm going to start stepping attenuation. Oh, sorry, go to attenuation. Yeah. Start stepping in here's the attenuator. I'm going to start stepping in attenuation. This attenuation is right at the front end. Okay, we'll go 2 dB at a time. Right at the front end. So we go 4, 8. Now what's happening here is, let's see, why am I not seeing this behave the way it should? Oh, I know why. Sorry. The spectrum analyzer does do one thing that we didn't have before. It compensates for the attenuation level, but that's okay. The spectrum analyzer is mathematically compensating for the attenuation level on the trace, which of course it couldn't do when I put in the explicit, discrete component. But we'll watch the signal to noise ratio here, nevertheless. I'm going to take this back. Okay, here we are back at 6 dB of RF attenuation. It's compensating, so this level is in reality coming down but it's just compensating for it on the trace. To put it another way, as I'm putting attenuation in here, the spectrum analyzer is compensating, although you can't see compensating, by bringing the overload threshold level up by a compensating amount. You just can't see that happening here. There's no visual display for that, but that is what it's doing. So we are helping ourselves. But now watch the signal noise ratio. We're starting off at 20 with 6 dB. Now we go to 8 dB, still 20. 10 dB, still 20. 12 dB, still 20. So see, we're able to keep padding that gain right on down. It's not even hurting our signal noise ratio yet. 14 dB, that's about where we were before, where we thought we were about optimal. I put in about 13. Now we're going to go to 16. Oop, just a tiny little touch. Did you see that?
Yeah.
Right there, the first little decrease in signal noise ratio right there at about 16. Ah, and then we can go 18. Let's see, we put in 2 dB of attenuation, only lost about 1 dB. Now, at 20 dB of attenuation, now we're starting to really lose signal to noise ratio. So that's not good either. So the sweet point here, where we kind of optimize our signal noise ratio, but we're also optimizing dynamic range, is at about 16 to 18 dB, just like we did with the manual attenuators. Perfect. Optimum for signal noise ratio and optimum in terms of dynamic range if you're trying to optimize both variables at the same time simultaneously, as opposed to if you were trying to optimize just one or the other. Okay, so this is the information that we bring to bear when we're designing any kind of radio receiver, any kind of measurement system. If we're using a spectrum analyzer, is that if we're trying to get, the bottom line is if we're trying to get amplification at the front end, we use the cascade gain equation, or you can do it empirically this way if you're trapped on a desert island. But what you try to do is get the lowest possible noise figure, at least a noise figure that's low enough to meet the need of your application or your sponsor or your research, with only enough gain to overdrive the noise figure of the measurement system or the radio receiver, but you really don't need any more gain than that. That's really what the whole thing finally comes down to. And now we know how to do it. One other useful little thing, if you're trying to optimize things right at the get-go and you don't have any desired signal to work with at all, and so I'm going to turn off the desired signal, turn that off, okay, and I'm going to take the spectrum analyzer's attenuation here down to 0 dB, like so. If I want to get the gain plus the noise figure of this amplifier to be about equal to the spectrum analyzer's noise floor, which means that the overall noise figure of the system will be 3 dB higher than the noise figure of the LNA. Again, what I can do is just pad the output on this LNA with some attenuators. We would want about 10, 23 dB of RF attenuation right here. So I screw together a pair of 10s, that's 20, and then I'll screw a 3 on, like so. And we've done this many times during field measurement scenarios. And then I'll turn off the power on the amplifier so I don't twiddle the power on these bare leads on the input and cause something bad to happen. Not that I haven't ever done that. And put in the attenuator right here. Now when I turn this amplifier on, I'm hoping to see the magenta trace rise about 3 dB above the yellow trace, right up to that minus 90 dB line, 2 divisions from the bottom. If I did my math right, it should be about right when I do that. Turn the amplifier back on. Yeah, I overdid it just a little bit actually. I've got a little too much loss in there. So that's all right. Just sit here and adjust it a little bit. See, at that point, my gain isn't really quite as high as I want it to be. So I'm going to take out a 3 dB pad. So now I got 23 dB. The reason I'm off a little is I was just adding the decibels. So technically I need to use the anti-logs to do it right, but I was just doing it in my head. So that's all right. It just takes you a second. Just takes you a second with a couple of attenuators to get this thing adjusted up properly. Okay, turn it back on. Okay, so I took out 3 dB. That's actually not bad. Instead of jumping up 3 dB, the noise level jumped up 4 dB. But that's okay because that means that the gain plus the noise figure of my amplifier is a little higher in decibels than the noise figure of the spectrum analyzer, but that means the noise figure of my overall system is actually beginning to approach the noise figure of my LNA. So that would be a good place to start then, if you then said, okay, now we're ready to start making a measurement, let's turn on that signal like that. Good place to start. So you don't have to have a spec sheet although it's nice to have a spec sheet, you don't you don't really have to have much of anything except the amplifier and some attenuators and the ability to watch this display like this, and take one first quick cut at it, put in some attenuators, maybe make a second cut, and there you are, ready to go. Again, you've optimized your measurement system at that point. You didn't even have to check a spec sheet. So again, people think not only can you read the noise figure spectrum analyzer directly off the display, but now they'll really be convinced that you have superpowers, because how did you do that? Takes years of training and practice. So no, I just twiddled the attenuators until when I turned on the amplifier, I saw it rise 3 or 4, maybe 5 dB above the noise floor I had before. I'm like, okay, that's good. That's right where we want to be. Ready to go. And that concludes the talk. Any questions or comments at that point? Okay, thanks for coming.